So yeah, it's my pleasure to have Alex Scott on our big seminar. He's a professor at Oxford and has various very interesting results in all parts of extremal combinatorics and not only. Today he'll talk about some applications of exterior algebra to extremal set theory. Thanks, Alex, for agreeing to speak.
Okay, thank you very much. It's delightful to be here, and not quite as good as coming in person, but fantastic to be here virtually. So, okay, so I'm going to talk about some joint work with Elizabeth Wilmer, who's at Oberlin College, and I think is also in the audience. So it's going to be I'm going to be talking about combinatorics and exterior algebra. And very much about the Two Families Theorem. So I'm not going to assume that you know anything about the exterior algebra, and so sort of with apologies to those who are algebraists or already expert on this sort of thing, I'm going to go through some very basic facts about the exterior algebra and try and convince everyone that it's a nice thing. So I'm going to start out by talking about the Two Families Theorem. I'll then set up some exterior algebra. I'll then talk about combinatorics in the exterior algebra and the kind of connection between certain bits of combinatorics and things that happen in the exterior algebra. And then I'll come back at the end to the Two Families Theorem again. So sort of the third part is going to be talking about using combinatorics to do things in the exterior algebra. And then the fourth part is going to come back and talk about using the exterior algebra to do things in combinatorics. Okay, right, so let's start by talking about the Two Families Theorem. So this is a beautiful theorem, one of my favorite theorems of Bailey-Bolabash from the 1960s. And it says the following. So I have some pairs of sets, A1, B1, up to AM, BM. And they satisfy, well, the AIs all have size little a, the BIs all have size little b, and they satisfy the conditions that the pairs AI, BI are disjoint. But AI and BJ, if I is distinct from J, they intersect. So you miss your paired set, but if you have two sets, an A and a B from different pairs, then they have to intersect. And the theorem says that in that case, there are at most A plus B choose A pairs of sets in our collection. Okay, so it's a lovely theorem. One thing that's lovely about it is that this bound doesn't mention the size of the ground set. So it's an arbitrarily large ground set, doesn't matter. The maximum number, though, is dependent only on A and B. So the theorem sort of come up in lots of different places. I should note it's also sharp. So here's an extremal example. Let's take a ground set of size A plus B, and as your pairs, just consider all pairs that consist of a set of size A and its complement. Okay, and it's quick to check that satisfies this two families condition, and obviously it has size A plus B choose A. Okay, so this is the original, essentially the original version of the theorem, and there are two types of generalization that have been carried out. So here's the first type of generalization. So we vary the sizes of the sets. So again, we have pairs A1, B1 up to AM, BM. Again, it's the same condition. So AI and BI have to be disjoint, and AI and BJ meet whenever I and J are different. And then the condition is that the bound is that the sum of the size of AI plus size of BI choose the size of AI inverse is at most 1. Okay, so this sort of weighted sum. So note that if all the AIs have size A and all the BIs have size B, so if we're back in the original set up, then this says exactly the sum of says exactly that there are at most a plus b choose a of them. So it's a generalization. Okay, so this is it's a very nice generalization. We'll refer to the ordered pair size of A comma size of B as the profile of the pair AB, just to have an easy way of talking about the pair of ordered pair of sizes of the sets. Okay, so let me show you a proof of this, very much the standard proof. So probably you've all seen this before, but if you haven't, it's a lovely proof. So so this is I think Lubel's method of counting things. It's also very similar to the Catenary circle method. So you consider your collection of pairs AI BI on some ground set, and just take a random permutation. Okay, so for any permutation pi, we'll write A as less than B in the order given from pi if the maximum of pi of A, so the maximum of anything under pi, anything in A under pi, is less than the minimum of anything in B under pi. Okay, and in a random order, what's the probability that everything in A is to the left of everything in B? Well, the elements of A and B come equally likely in any order, and there's one of the orders that works. So it's size of A plus size of B choose A inverse. Okay, and then you just note that the events that AI is less than BI, these events are disjoint. Why are they disjoint? Well, look at the condition. You can't have A1 less than B1 and A2 less than B2 because A1 has to meet B2 and A2 has to meet B1. And if you check, that means that you can't have it both ways. Okay, good. So it's a very short, sweet proof. Okay, so that's one generalization where we allow the sets to have different sizes and weight them. Okay, so here's a second generalization. So now we go back, so due to Lovas, now we go back and insist that the A sets all have size A and the B sets all have size B. So now it's sort of the profiles are all the same. We keep the condition that AI and BI are disjoint. But now we have this, we weaken the intersection condition. So rather than every AI meeting every other B, we have that AI and BJ meet if BJ comes later in the sequence than A. So earlier A's meet later B's. So if I is less than J, then AI and intersect BJ is non-empty. Okay, so this is a skew intersecting condition. And under this skew condition, we still keep the original conclusion. So we keep the property that the number of sets is at most A plus B choose A. Okay, so it's another very nice, lovely generalization. And I'll say the proof uses exterior algebra. Okay, and I'll tell you the proof, but in a few minutes. So we'll need to talk a little bit about exterior algebra first. So let's note we've got two ways of extending the two families theorem. So one is to allow different profiles, and we get a weighted sum. And the other way is to weaken the intersection condition, so have a skew intersection condition rather than this sort of complete intersection condition. Again, it's a natural question to ask, and various people at various times have asked it. Can we do both? So is there some generalization that has both these properties? Okay, and actually this was the starting point in our search. We were thinking about this question and trying to push the exterior algebra method. Well, we tried both, but we were trying particularly to push the exterior algebra method to see if more could come out of it. Okay, so let me talk about the exterior algebra method. So let me give you an abstract slide, and then I'll be much more concrete on the next slide. So let's start with a vector space Rn, R to the n. And okay, so this is just here as kind of due diligence in some sense. So the exterior algebra, it's the quotient of the tensor algebra by the ideal generated by V tensor W minus W tensor V. Okay, so this is something you sort of stick in to have an alternating property in your exterior algebra. I'll come to that in a second. I just want to say there's a kind of completely formal way of writing it down very briefly. And it has this sort of universality property that if you have any alternating map from a product of k copies of a vector space to the real numbers, then it factors through the kth exterior power. Okay, maybe I won't say more about that. I'll just say this sets it out formally. But let me give you a concrete version that maybe is sort of more hands-on. By the way, if you read this in most algebra texts, it will give you the formal version in terms of kind of alternating multilinear maps and tensor algebras and so on. Usually, sort of the algebra approach avoids very concrete writing things down in terms of specific bases. The best presentation in those terms that we found, I think, is if you read it up in Bourbaki, then Bourbaki has a very, very nice, very concrete, everything written down presentation. But you have to read the first edition of Bourbaki, the 1940s edition, because it got rewritten in the 1970s and it's way more abstract. And of course, it does much more. But if you want to really know about the basis specific things, then and have it much more concrete, then the first edition is the place to look. Okay, so then let me actually come down and say some things. So it's going to be very convenient for us to work with a specific basis. So let's just E1 up to En be the standard basis for Rn. And the kth exterior power, so now let me give you something very concrete. So it consists of linear combinations of elements of the form V1 wedge ... wedge Vk. So you just take k vectors and write wedge symbols between them. Okay, and I have to give you some rules for when these things are equal. So you take a sum of these things. How do you work with this? So so it's multilinear. So if I take a plus 2b, wedge it with c, I get a wedge c plus twice b wedge c. So I'm telling you completely elementary things, but and linear in every variable. So I'm just giving you the wedge of two things here, but it's the same in the wedge of k things. It's alternating. So if I take a wedge b and flip the order, that's minus b wedge a. More generally, if I take v1 wedge vk and I reorder them, I get plus or minus one. Well, the sign of the permutation tells me whether it's a plus one or a minus one. And if I wedge something with itself, I get 0. Okay, so these are sort of basic rules, and you just have to believe that this thing, an object with this property exists. The previous slide guarantees that it does exist, and that's a construction. Okay, let's see what else. V1 wedge ... wedge Vk is 0 if and only if V1 up to Vk are linearly dependent. So you can think of a wedge of k vectors as in some sense encoding the subspace that they span together with an orientation. Okay, so and if they don't span a subspace, a k-dimensional subspace, so if it's a low dimensional subspace, then you get 0 as the wedge. Okay, and for that reason, if k is larger than n, the dimension of your underlying vector space, then the kth exterior power is 0 because you're wedging together more vectors than you have dimensions. So there has to be linear dependence. Okay, so the kth exterior power has these various properties. Let's carry on. What about a basis? So it's nice if you can take things back to a basis. Well, if we just going back a second, so if I think about V1 up to Vk wedged together, I could write Vi as a linear combination of E1 up to En, and I can use multilinearity to expand it out. And so I get everything coming as a linear combination of wedges of k standard unit basis vectors. Okay, so that's what this first bullet here says. The kth exterior power, so kth exterior power because we're wedging together k things, it has a basis, all the things you get by wedging together k distinct vectors from your basis. Okay, and I'm choosing to have them in increasing order for convenience because the order does matter. Okay, the dimension is clearly then n choose k because it's just a number of choices of k out of n vectors. So okay, so that's the basis. And by the way, the full exterior algebra is just a sum over all k of these things. Okay, right. Now, given a set, and this is going to be very important, given a set A, we can define a corresponding wedge product. So you just take the elements of A and wedge together the corresponding EIs. So if A is 1, 2, you get E1 wedge E2. Okay, so if A has size K, then the corresponding wedge is in the kth exterior power. Okay, now I've written plus or minus the wedge product of the EIs, plus or minus again because the order matters. And of course, you can everywhere here, you can write down whether it's plus or minus. I'm generally just going to write plus or minus to avoid having lots of extra sort of little bits of notation floating around. Okay, so for convenience, I'm just writing plus or minus. And on the right, I've actually written, so 1, 2 corresponds to E1 wedge E2 or minus E1 wedge E2. That's the only difference between taking E1 wedge E2 or E2 wedge E1. Okay, so you get the same vector up to plus minus 1 factor. Okay, and you can also multiply these vectors together with the wedge product.
Sorry, just a little clarification. So here, this sign, what does it depend on? So it depends on A, but like, what do we need to know from?
Okay, so I'll take EA to be order the elements of A in increasing order.
Yeah.
And then take wedge things together in that order.
Yeah, and with plus, and that would be with.
Yeah.
Okay, okay. So it's not about the A. It's really okay. Okay.
Yeah. So really, 1, 2 goes to E1 wedge E2. 2, 1 would also go to E1 wedge E2 because we'll sort them first. Yeah.
Okay.
So the order it's written down in doesn't matter. Okay. Yeah. That comment's maybe slightly more important for the next bullet. So we can multiply two things together with this wedge product. So if I take something in the 8th exterior power and something in the bth exterior power, then their products in the A plus bth exterior power, what do? You take the first wedge product, the second wedge product, just write them down with a wedge in between. Okay, so take the product of them all. And this extends by linearity to, so remember, the kth exterior power is actually all linear combinations of these things. So rather than taking just V1 wedge ... wedge VA, I'll take some linear combination of things of this form. Okay, but here's how it works on just wedging two things together. You get that. And again, if you're taking EA and EB, so if you have sets A, B, and you think about the corresponding EA and EB and wedge them together, well, you're going to get plus or minus E A union B because you're sorting A and B. So again, formally what's happening, if you write A in increasing order and B in increasing order, then the sign is the sign of the permutation that sorts them together into sorts the concatenation into increasing order. Okay, but that's a technicality we don't have to worry about if we just write a plus or minus and makes it simpler. So here we are, EA wedge EB is plus or minus E A union B if A and B are disjoint. If A and B intersect, we get 0. Why? Because then we have a repeated element. We know that if you wedge something with itself, you get 0. And in fact, or equivalently, if there's a linear dependence in the things you're wedging together, then you get 0. And in EA wedge EB, so yes, if the same vector occurs twice in the wedge product. Okay, maybe that's a good point to pause for a second and say, are there any questions? I'm going quite quickly, so. Okay, good. Right, one caution. So let's say when you first, if you haven't met the exterior product before, it's natural to expect things to be decomposable. What does decomposable mean? It means you can write them as a wedge of some vectors. So X is decomposable if you can write it as V1 wedge ... wedge VK. So if it can be written in that way for some choice of V1 up to VK. And the caution here is that most elements are not decomposable. Okay, so this is why the exterior algebra is much more complex than it first appears, because you have all these non-decomposable elements. And certainly for me, my intuition works much better for decomposable things. Okay, so it's a more immediately geometric. So you have to be a little careful sometimes. Okay, and then if you want a nice exercise, you can check that this is not E1 wedge E2 plus E3 wedge E4 is not decomposable. Okay.
I guess maybe it's one can say that it's like a rank of a matrix in the situation, right? So it's like matrices of rank 1 are decomposable, and in a similar way. Yeah.
Right, but linear combinations of such things are not.
Yeah.
That's fair enough. Yes. Okay, so let me remind you of the skew version of the two families theorem. So we had the A sets and B sets in pairs. Each pair is disjoint, and then if I take an earlier A and a later B, they meet. So this was the skew condition, and we want to show this at most A plus B choose A of them. Okay, and there's this beautiful proof. So so I should say I'm going to try very hard to convince you this is a beautiful proof. So for me, I first saw the exterior algebra in some algebra class, and I guess you see it as well in when you do differentiable manifolds. But I first thought it was actually really nice when I saw this proof. So okay, so here's the proof of the skewed two families theorem. So I've just written the conditions up in the top right hand corner. So let's for our vector space, let's take the A plus B dimensional real space, RDA plus B, and we'll choose some points V1 up to Vn, so corresponding to the ground set. We'll just throw them in general position. So no linear dependencies other than the ones that absolutely have to be there. So any A plus B points from this collection should be linearly independent, and if you just throw them in at random with any reasonable distribution, that will do it. Or you can write down explicit ways of doing that too. Okay, and now we'll map each of our sets to elements of the exterior algebra. We've got V1 up to Vn in general position, and so let's define a vector ui by wedging together the corresponding vj's. Okay, so for each element of the set AI, we wedge together the corresponding vj. So you've got a different vectors v that are being wedged together. So we're in the 8th exterior power. And for bi, we do the same thing. We wedge together the corresponding vectors, and we get something in the bth exterior power. Okay, so we get some things. And let's note, these are non-zero. Why? Well, we chose points in general position, so the A points that we're wedging together to get UI are linearly independent. So we're going to have something that's non-zero. And similarly for BI, the B points that we chose, because they're in general position, we know they're linearly independent. Okay, so we can certainly get non-zero vectors. What about the wedges between them? So if I wedge together UI and WI, so vectors corresponding to a pair, so up to this plus or minus sign that comes from the reordering, I'm wedging together everything in AI union BI. Okay, so that's A plus B vectors in total. Again, general position tells me that they are linearly independent. So I've got a linearly independent set of A plus B vectors. So I get something non-zero when I wedge them together. Okay. What about UI wedge WJ? Well, when I wedge together UI and WJ, there's a common element to AI and BJ, if I is less than J. So when I wedge everything together, I've got some vector that occurs twice, and that tells me that the wedge product is 0. Okay. So again, the properties I've got, let me move to the next page. So we've got some vectors UI in the 8th exterior power, WI in the bth exterior power, and all we need is that UI wedged with WI is non-zero, and UI wedged with WJ is 0 when I is less than J. Okay, so that's what comes out. Okay, good. And now the rest of the proof is actually very easy. We're just going to use this to check that the vectors UI are linearly independent, and then just make a dimension argument to say there can't be too many of them. Okay, so why are they linearly independent? So this is absolutely bread and butter now. So suppose that you have some non-trivial linear combination giving you 0. So let's take the maximum I such that lambda I is non-zero, and I hope I've written the right way around. It's either maximal or minimal. So here it's maximal, and that's wedge with WI. The point is WI kills off all the earlier UIs, and only UI survives. So sigma lambda uj wedge WI, So by linearity, that's sigma lambda j, uj, wedge wi. Only ui, wedge, wi survives, the others are all 0. And this has to be non-zero, and that's a contradiction. Okay, because we started out with something that was 0, wedge, wi. Okay, so that tells us that we do have linear independence. So the number of pairs is at most the dimension of the underlying space. What's the underlying space? It's the 8th exterior power. And we know that the 8th exterior power of Rn has dimension n choose a, or in this case, a plus b choose a, as we're in R, a plus b. Okay, so that was done at fairly high speed, but again, the key idea is you're mapping your sets to a suitable exterior power. This general position is a nice trick to get as much independence as you can while keeping the ambient dimension as low as possible. So you're crunching down the dimension as much as you can while keeping the points linearly independent. And then this checking that you have wedge product 0 or non-zero accordingly. Okay, so that's the proof of the skew version of or one proof of the skew version of the two families theorem. There are other proofs as well. There's a nice polynomial proof too. Okay.
Yeah, actually, this is what I wanted to ask. So the other proof uses symmetric, like polynomials, actually.
Yes. Yeah.
Okay. So it's
my suspicion is that I've sort of not sat down and really absorbed whether it's exactly the same in some. So it feels kind of similar. I mean, it's different but similar in some sense.
Yeah, but
it's a lovely proof too.
But it doesn't work for some generalizations, right? So there are these subspace settings, and for that you need exterior, for some of them at least, right?
Yeah. Yeah. I mean, the exterior algebra language is better configured to handle subspaces as well, because these things actually talk about wedge products correspond to a wedge product of some vectors does correspond to a subspace. So then you're in some sense in good shape.
Okay. Thank you.
Okay. Right. On to the next bit, combinatorics and exterior algebra. So this is the third part. All parts of the talk are not equal, by the way. So now it's going to slow down a little. Okay. So we've got our exterior algebra. I hope anyone who isn't comfortable with exterior algebra already, I hope I've given you some feel for what it looks like a bit. I think you should think of it as a vector space, but this wedge thing means there's all sorts of kind of skew stuff going, funny stuff going on. Okay, so the rough idea is going to be the following. So we've got a ground set 1 up to n, and on sort of the exterior algebra side, so the left-hand side is combinatorics, right-hand side is algebra. I want to think about the vector space Rn. And so element of the ground set, I want to think of corresponding to the ith standard unit basis vector, EI. And remember, an R set A corresponded to the wedge of the corresponding EIs. Okay, with a plus or minus, but I'll leave that out. Okay, so if I have a R uniform set system, so each R set corresponds to something in the rth exterior power, some wedge of R basis vectors. So if I have a collection of R sets, I can think of that as corresponding to a subspace of the rth exterior power. Okay, now I should emphasize that the subspaces we're getting here are very nice subspaces because they're spanned by decomposable vectors. So all the vectors that come from these R uniform set systems, or from these R sets rather, are decomposable because we've written them as a wedge product of some vectors. But a general subspace won't have lots of decomposable vectors in it. Okay, so this correspondence gives us very nice subspaces. Okay, nevertheless, we'll see that those are in some sense very helpful to think about. Okay, and now the crucial thing, if I have two sets that intersect, then what do I think about on the exterior algebra side? Intersection for sets is analogous to having wedge product 0 on the exterior algebra side. Okay. Right. Okay. So we've got this kind of correspondence going on, and what I'm going to do is sort of try and show that it's useful in both directions. Okay. So I should say we're not the first people to do this. There's other people who thought about similar things, but maybe I'll come back and say more about that later. Okay. So let's start with a. I think this is a nice theorem. So suppose we have, again, so V, our vector space is Rn, and R is going to be less than at most n over 2. And suppose we have some subspace that is has the property, so some subspace of the rth exterior power, so that every pair of vectors has wedge product 0. Okay, totally straightforward, basic question. So this is a warm-up result. Totally basic question. What dimension could that subspace have? Okay, so I mean, if you were dealing with a bilinear form or something like that, you know, these questions you study in algebra, and we looked for, we tried to find this, was this well known, and we couldn't find it anywhere. So, okay, so the question is, what's the largest subspace of the rth exterior power, which so that every pair has 0 wedge product? Okay, well, the answer is it's at most n-1 choose r-1. Okay, and of course, probably everyone now knows exactly how I'm going to do this, exactly what theorem I'm going to mention in a minute. Okay, so in order to do this, we'll have to talk about some combinatorics. Okay, so colex. Let me remind you about the colex order. So recall the colex order. So you have two sets A less than B. So it's an order on R sets, actually more generally, but let's just think about it on R sets. So A less than B if the maximum element of the symmetric difference is in B, or equivalently, if you sum 2 to the I, or any reasonably fast-growing function over A, that's smaller than the sum over I and B, 2 to the I. Okay, so large elements sort of rule everything. Large elements are in charge. Okay. Okay. So when we take a basis, and remember we're generally going to be using just this standard unit basis, these EIs, we'll order them, and we'll order the basis EA. Yeah, so the basis consists of all R sets, or corresponds to the collection of R sets. We'll order them by colex order. So, for instance, for n equals 4 and I equals 2, so if we have the second exterior power of R to the 4, so we've got our 6 4 choose 2 basis vectors, and they come in the order E1 wedge E2, E1 wedge E3, E2 wedge E3, E1 wedge E4, E2 wedge E4, E3 wedge E4. So just in colex order of the subscripts, in other words. Okay. By the way, when we thought about doing this, we were kind of very, very happy, but and very proud, and then of course we realized that other people have done this. So people that study monomial algebra, monomial ideals have done this, and people that study Grosvenor bases, and so very much this is well-trodden ground. We're going to use it to do some different things. Okay, now right. So given a vector, so sigma lambda A EA in the rth exterior power, let's define the initial set just to be the smallest set where the corresponding basis element has a non-zero coefficient. So you look at the earliest non-zero coefficient, that's the one you're interested in. So the initial set of V is the smallest A in colex order, so that lambda A is non-zero. So for example, here we have 4 E1 wedge E3 plus 3 E2 wedge E3 minus E1 wedge E4. So the earliest of these 3 in colex order is E1 wedge E3. So that'll give me the set 1, 3. So we're interested in which basis element has the earliest basis element that has a non-zero coefficient, and which set does that correspond to. Okay, so that gives us a mapping from vectors to sets. And now if I have a subspace, so W is a subspace of the rth exterior power, I can talk about the corresponding initial hypergraph. And that's just everything I get by taking initial vectors of elements of my subspace. Okay, so it's a sensible thing to do. What does it give you? So here's the nice thing. If I take a space W and say how large is the corresponding hypergraph, well, the number of edges is dimension of W. Okay, so a d-dimensional subspace gives us a hypergraph with d edges, which is kind of really helpful. And the proof is actually very simple. Let's just take a basis for the subspace W, and let's write it in row-reduced echelon form. Okay, so here we are. Here's my basis, B1, B2, B3, or my basis after turning it into row-reduced echelon form. So in each row, I've got a 1 somewhere, and they come later and later as I go. And we just note that if I take any linear combination of these, the earliest non-zero coefficient is always going to be in one of these columns where we have a 1. Okay, so the initial subset of any vector in this space is one of these columns where we have an initial 1. Okay, and that's exactly the number of basis vectors. Okay, so it's very easy, but it's really helpful that dimension carries across to the size of the hypergraph. Okay, so what this gives us then is a mapping from subspaces to hypergraph, preserving size in some sense, so of dimension and cardinality. Right. Okay, second useful thing, if we have V and W, so two elements in the Rth exterior power, and these may not be nice decomposable elements, so they've got arbitrarily nasty things. But suppose they have wedge product 0. I claim that the initial set of V and the initial set of W have non-empty intersection. Okay, so it really does say that having wedge product 0 does in some sense correspond to at least some pair of sets intersecting. Okay, and again, the proof is not too hard, so let's write V and W, just expand them in the basis. And let's say I'm writing my basis in this colex order. So lambda A, EA, so EA is the earliest basis vector with a non-zero coefficient, and then EB for W is the earliest basis element with a non-zero coefficient. So the initial set of V is A, the initial set of W is B. And let's suppose that A and B are disjoint. Okay, so I'll just show then that V wedge W is non-zero. Okay, so if I take V wedge W, well, it's just a linear combination of everything in the linear expansion of V and everything in the expansion of W. So we know that the first term that comes out is the wedge of lambda A EA and mu B EB. So here we are, contains the term lambda A mu B EA wedge EB. Okay, and that's non-zero as A intersect B is non-empty. So is empty. A and B are disjoint. Okay, so there must be some other term, since if the wedge is going to be 0, there must be something else that gives us a multiple of EA wedge EB, which is A union B, remember. Okay, so there must be some F and G with F union G equal to A union B, so we have to get it from somewhere else. And non-zero coefficients. Okay, but F has to occur at least as late as A in the colex order, and G has to occur at least as late as B in the colex order. And we can check that's impossible. We can't get the same union again. Why? Well, the sum over we can't have F equals A or G has to be equal to B. So actually, they both have to come later. So that tells us that sum over I and F of 2 to the I is bigger than the sum over I and A of 2 to the I. So this was just writing on one of the definitions, one of the equivalent versions of the definition of being later in colex. And similarly for B, sum over 2 to the I over G is bigger than the sum over 2 to the I in B. So we can't have A union B as F union G. Okay, it's a contradiction. Okay, so this says then that if I have wedge product 0, then my initial sets must intersect. Okay, which is again helpful. Sorry, let me just go back and forward a second, remember where I am. Okay. Okay, so let's now prove this. So, and now the proof is actually very short and has the expected name at the bottom. So Okay, so we've got a subspace of the Rth exterior power such that every pair has wedge product 0. And we claim that the dimension is at most n-1, choose r-1. Okay, well, we know that the initial sets, so the initial hypergraph for W, so everything we get by taking initial sets, gives us, that must be intersecting, gives us an intersecting hypergraph. Okay, well, dimension of W is this, remember that it preserves size. So the size of the number of sets in the intersecting hypergraph is equal to the dimension of W. But the Erdős-Coe-Radó theorem tells us that we can't have more than n-1 choose r-1 sets in our intersecting system. Okay, so it's a very, very short proof. Of course, as since you're applying Erdős-Coe-Radó, you expect to have r at most n/2. Just as an aside, what happens if r is bigger than n/2? Well, then v wedge w would, if v and w were in the Rth exterior power for r bigger than n/2, then the wedge product would have to be 0, because I'm taking, the basis vectors would correspond to sets of size r. When I wedge together, I'm wedging together 2r elements. I'm taking linear combinations of those. And if 2r is bigger than n, then I have to have wedge product 0, because after the nth power it's 0. Okay, so it corresponds very nicely to Erdős-Coe-Radó. Okay, right. Just as a kind of side remark, when do you get equality? So if r is less than n/2, well, okay, in general, you attain equality if you take all things that form v wedge z, z in the r-1 exterior power. Okay, so you take any vector v and then wedge it with the r-1 power, and the dimensions work out. And actually, we conjectured independently, Woodruff conjectured that all extreme examples are of this form for r less than n/2. And I'll just say, kind of as an aside, we actually now do have a proof of this. So it kind of uses similar ideas, but some additional arguments. And yeah, you use a kind of slightly different technique, but very much a extremal set theory, extremal combinatorics technique. Good. Right. Yeah, natural thing to ask. Okay, first we have one subspace where all products were 0. What if I have a pair of subspaces where U and V, where everything in U wedge everything in V is 0? So again, it's going to go exactly the same way. So I claim that dimension of U times dimension of V is at most n-1. So if U is a subset of the Rth exterior power, W is a subset of the S exterior power, then the product of dimensions is at most n-1 choose r-1 times n-1 choose s-1. Okay, so the proof is very much the same. So you pass to the initial hypergraphs. So you have initial hypergraphs F and G. F has size dimension of U. G has size, sorry, I should say dimension of W. And if I take anything in F and anything in G, they intersect. So I have a cross-intersecting pair. And then there are old results of Matsumoto and Tokushige or Piba that tell you that the product of the size of F and the size of G is at most n-1 choose r-1 times n-1 choose s-1. Okay, so it comes out exactly the same way. Curiously, as I said, we did look and couldn't find these results in the algebra literature. Whereas sort of, with combinatorial tools, they're very natural. So, okay. I claim that's a good point to break. So we've kind of cantered through a whole bunch of exterior algebra. So I've got a couple of more results to translate from combinatorics into the exterior algebra, and then we'll turn it around and come back into combinatorics again. Okay, so right, so we just finished talking about subspaces where the product is always 0, and pairs of subspaces which are kind of mutually annihilating. Okay, so let's think about another combinatorial operation. Let's think about the upper shadow. So let's just remember that the upper shadow of a set F is just everything you get by adding something to elements of your set. So it's all sets of form F union X, where F is in your set system and X is not in little f, not in F. Okay, so if F is a collection of R sets, that's Same thing as saying all R+1 sets that contain something in your system. Okay, and the local LYM inequality says that if I take the upper shadow, then the fraction of the R+1st layer contained in the upper shadow is at least as much as the fraction of the rth layer contained in the original system. Okay, so it's an easy but very useful result. Okay, and you can prove it by double counting or by random chains or whatever. Okay. Right, so what about in the exterior algebra? So it'd be nice to have some analog of this. And okay, so if you think about subspaces that come from set systems, so if I have, say, E1 at wedge E2, and I want to add 3 to that, I would wedge with E3. And more generally, what seems to be a good analog is, so for a subspace U of the rth exterior power, we'll write U wedge V for everything you get, so the linear span of everything you get by taking something in U, something in V, and wedging them together. So this is analogous to adding an element, we're wedging with a vector. Okay, and it works nicely with size, because if we wedge with V, so we're taking some elements of the rth exterior power, we wedge with the vector, we get something in the R+1st exterior power. So this takes a subspace of the rth exterior power, gives us a subspace of the R+1st exterior power. And you can check that if you take a set system F and take the corresponding subspace of the rth exterior power, so just for each vector, again, for each set A, you take the corresponding wedge of EIs, and then do this, you get exactly something that corresponds to the upper shadow. Okay, so it works for that, and then more generally, we just define it as everything you get for wedging with something of the underlying space, and then linear combinations, so whatever that spans. Okay, so this is our definition of something analogous to the upper shadow. Okay, so here's the theorem. So again, I've just written the definition back at the top. So the theorem says that if I take U wedge V, so U is a subspace of the rth exterior power, and remember our V has dimension n, then dimension of U wedge V divided by n choose R+1 is at least the dimension of U over n choose R. Remember, n choose R is the dimension of the rth exterior power, n choose R-1 is the dimension of the R+1st exterior power. So the fraction of the dimension that we get in our subspace, fraction of the dimension of the whole space goes up every time we wedge with V. So it's just like LYM, but in the exterior algebra. Okay, and if I say that the proof again uses initial sets in our local LYM, if I gave you some time, you would probably guess exactly how we're going to do it. But let me show you. So, okay, so let's say we have a subspace of the rth exterior power, and let F be the corresponding initial set. Okay, so U, using this initial set function, gives us our set system F. If I take U wedge V, I'll get some other set system G. Okay, so F is an R uniform hypergraph, G is an R+1 uniform hypergraph. And what I want to claim is that when we wedge with V, then what we get, well, the initial set for U wedge V contains the upper shadow of the initial set for F. So the claim is that the upper shadow of F is contained in the initial set, initial hypergraph for U wedge V. Okay. Now, if U actually came from some set system F, so if it was nice, sums of nice types of vectors, then actually we'd have equality. But in general, these subspaces sort of point in all sorts of different directions, and it's not the case. Okay, if the claim is true, let's just see why this exterior algebra version of local LYM holds. So we're interested in the dimension of U wedge V divided by the dimension of the R+1st exterior power, n choose R+1. So by this initial set property, the dimension of U wedge V is the same as the size of G, number of edges in the initial hypergraph, divided by n choose R+1. And that's at least, by the claim, is at least as big as the upper shadow of F, divided by n choose R+1. And now local LYM says, well, that fraction's at least as large as the fraction of the R layer we had in F, and that was the dimension of U divided by n choose R. So it just follows straight through. The key thing is just checking that when you move to the initial set, if you wedge and move to the initial set, then that contains what you get by moving to the initial set and then taking the upper shadow. Okay, so let's just check that. And it actually is very much like arguments we've seen already. So it's not to prove the claim. So let's suppose we have something in the initial set of U and I is not in A, and we'll just check that A union I is in the initial set of U wedge V. Okay, so if we wedge and take the initial set, then we have to that has to contain A union I. So we're just taking an arbitrary element of the upper shadow. Okay, so, well, A had to come from somewhere. It was the initial set of some vector U. So there's some vector U, which is lambda A EA plus some later terms in colex. So later terms in our order. So remember, our basis is in colex order. Okay, so what happens when we take the initial set of U wedge EI? So I claim the initial set of U wedge EI is just A union I. Okay, why? Well, we know that when we take U wedge EI, it starts out with EA wedge EI, which is A union I. I've actually missed out a plus or minus here, depending on whether I is where I is relative to the elements of A, but again, that's just a technicality. And the later elements, well, I just claim the later elements are either going to be 0 because I'm wedging I with some EB where B contains I, and that'll give me 0. Or they'll be later in colex because B is later than A, so B union I has to be later than A union I. So if I just add the same thing to both sides, it's not going to affect which order they are in colex. Okay, so it's an easy check that this works, that A union I is the initial set of U wedge EI. Okay, so that tells us that if I take initial set and then upper shadow, everything I get is contained in what I take if I wedge with V and then take the initial set.
Alex,
So
can I ask you a question here? So you write inclusion, isn't it an equality really?
I don't think so. So right. So I could wedge with something that's in A, and that might kill A. And so if I have, for instance, EA plus EB, I could wedge with something in A. So the initial set is just A. And I could wedge with something in A that's not in B. It'll kill A and give me B union I for something.
Okay, so yeah, because you allow wedging with everything, and yeah, okay, with no restriction. Okay.
Yeah. And that's a feature of the fact that the vectors that we've got may not be decomposable. So yeah.
Yeah,
okay.
Yeah, that's interesting. Yeah.
Okay, let me just mention in passing that you can write this in terms of graded algebras. I think maybe I'll just mention that this is here. I'm not going to talk about it. So you can split up the full exterior algebra as a sum, and if you have a graded ideal in the exterior algebra, you can look at the sort of minimal elements that generate, and we get some bound on those. Okay, so I'll just skip over this and get to the other version of local LYM. So that was we've done upwards version of local LYM. What about downwards? And this is trickier. So for this we need another operation, the interior product. Again, that's something that you just see slightly less often. It's sort of standard, but you see it less often, certainly in the combinatorics literature. So I think I've seen Oleg Pekerko use it and one or two other people. So what does it do? So it decreases the dimension, and it's analog for deleting something from a set. So taking the lower shadow, you want to delete things in all ways. So you want some operation on the exterior algebra that will do something similar, and that's the that's the interior product. So essentially what we're doing is we take some element of the, let's say a wedge of some vectors, so v1 up to vk wedged together. And now we hit it with something from the dual space v star. Okay, now you have to be a little bit careful with definitions at this point. If I'm going to have v star hit, so sort of some, let's say w star, let's say some w star hits v1 ... wedge vk, I've got to sort of decide where it's going to hit. So what you actually have to do is take a sum of all possible ways it can do it. So that there's a summation sign come in, and more generally, if you take a wedge of several copies of v star and hit a wedge of several copies of v, then you're going to have to do things in all sorts of possible ways. Okay, so I'll say there's some technicalities in writing down the definitions.
But so, is it exactly the same if you start with the tensor product, hit there, and then symmetrize somehow, or not? Like, can you express it in these terms?
Let me not even try to.
Okay.
It's just you have to write lots.
Let me speak. I think the answer is yes, in sort of the same way that you can do the regular wedge product in terms of the symmetrizations, and it's exactly the same kinds of issues. I mean, this is what gets called contractions in differential geometry usually. And I guess, Alex, one tiny clarification: when you say decrease the dimension, I think you mean decrease the grading degree in the exterior algebra. So it moves you, if you interior product with v star, it moves you from wedge r to wedge r minus 1.
Thank you, Elizabeth. Yeah, no, you're absolutely right. I should reserve dimension for the dimension of the space rather than I'm talking about the power. So it takes us from the rth power to the r minus first power. Thank you, Elizabeth. Okay, so I'm not going to go through this in detail because it's technical. I'll just say that if I have some subspace of the rth exterior power, and then I could hit it with v star, that reduces me from the rth exterior power to the r minus first exterior power. So I won't use the word dimension for that. And we get exactly the statement that you'd expect, which is the fraction of the r minus first. So in dimension terms, the fraction we get of the r minus first exterior power is at least the fraction we had of the rth exterior power. Okay. Okay, and I'll just say this: we use this to resolve conjectures of Gerbner et al. On the maximum size of the two-family system, where with an intersection property, and a special case was independently proved by Yu et al. So they use our framework in a slightly different way. Okay, so there's a nice paper by them as well. Okay, good. Right, so this is mainly to point out that there is an analog of the downwards version of local LYM. It works nicely, slightly more technical definitions, but it is fine. And the interior product is actually a nice thing. But you have to set it up carefully. Actually, it's almost easier, as Elizabeth says, you can look at it in this sort of abstract way. When you write down everything in terms of coordinates, you have to be very careful, particularly with the minus signs. So keeping track of that takes just a little. It just takes care, but it does take care. Good. Okay. Let me come back to the combinatorics.
Alex, maybe one last question about that part. So what about Kruskal-Katona? Natural question. Is there any meaningful analog of that?
Yes, absolutely. Yeah.
Of Kruskal-Katona for this setting?
Yeah.
So you
I mean, in some sense that's already known. So
but
some of this stuff can be read off Kruskal-Katona type things.
So you would have like a bunch of subspaces, and then you would do, because this is how it would look like if your subspaces, right? Or
yeah,
or I don't even, yeah, it's or you have your subspace and then you apply this So yeah, I don't know. So what would be even the
okay? Let's postpone that to later. Actually,
okay,
so,
okay,
yeah,
okay.
let me go to the end.
Sure.
Okay, so let's come back to the two families theorem. So suppose we have our family satisfying a skew intersection condition. So the first thing you might ask is, do we get the weighted conclusion? So can we just take the two extensions and just put them together and get the same conclusion? Okay, so sort of you might be hopeful, but the arguments but actually the answer is no, and actually not just bad; it's about as bad as it could possibly be. So here's the sort of standard example. So you consider all pairs A and A complement, and you list them in decreasing order of the size of A. Okay, so here we are. If n was 3, I take 1, 2, 3, then 1, 2, 1, 3, 2, 3 in any order, 1, 2, 3 in any order, and I guess I should take empty set and 1, 2, 3 at the end, which I missed out. Okay, and then this order satisfies the skew intersection condition, but it contains all pairs. So the sum of 1 over n choose A actually gives you n. So it's not bounded by 1 at all. It goes kind of catastrophically wrong. Okay, so
is it n or n plus 1?
N plus 1. Sorry, yes. Quite. Yes, you're right. Yes. In this case, n, because I missed out empty set and everything. So we need some more restrictions to make it true. So we can't just have an arbitrary sequence of profiles. So the question is, what sorts of restrictions will work? So we know that if we make all the profiles the same, that works. So here's a different thing you could do. So again, here's a new version of the two families theorem. So pairs are disjoint. Earlier A's intersect later B's as usual. And now the constraint is that the size of the A, so we ordered them, so the size of the A's is going up and the size of the B's is going down. Okay, and in that case, we do get the weighted conclusion. Okay, so I'm going to kind of sketch the kind of broad ideas of the proof, but I'm not going to go into the details. So actually, let's start by just sort of recalling the Lovas proof of the skew version of the two families theorem. So that's when the A's all have, the sets AI will have size A, the sets BI all have size B. But let me kind of phrase it in a slightly different way. Okay, so let's start with our usual vector space R to the n. So it's R to the n rather than R to the A plus B for the moment. So kind of a nice big vector space. And let's, as usual, map AI to EAI. And let's think about the subspace W that they generate. So it's a collection of, so the A's give us elements of the 8th exterior power of V, and we've got linear combinations of these. So this is a nice subspace, and we can use the BI's to show that actually the dimension of this subspace is indeed M, the number of sets we have. Okay, so why? Well, EA wedge EBJ, so EA wedge EB, it's 0 if I is less than J because there's a common element, just as before, and it's non-zero if I equals J because they're disjoint, and we're in a huge vector space anyway, so there's no issues with linear dependence. Okay, so sitting in the big space, we have an M-dimensional subspace. And now let's map down. So now we shrink the whole space, the underlying vector space. We shrink it to an A plus B dimensional space. So rather than Rn, we're now just going to take a general mapping from our vectors E1 up to En into R A plus B. In fact, a random mapping again will do. Okay, so what happens to the various things we've got floating around? So V maps to R to the A plus B. Okay, that's just our projection that we're taking. And I claim A plus B is the right dimension. That's the sum of the sizes of the sets. Okay, the 8th exterior power maps down to the 8th exterior power of R to the A plus B. and you can check that everything kind of commutes in the ways that it should. And then U maps to some subspace of R to the A plus B. And then the things we have to check are that the dimension of pi of U is the same as the dimension of U. In other words, we don't lose anything when the dimension stays the same when we map down. And that's true because these conditions on the wedge products, because we've taken a general position mapping or random mapping, these survive the projection. Okay, the dimension is just large enough for them to survive. And that's why we need A plus B as at least A plus B as the dimension of our space, underlying vector space. On the other hand,
here U is V, U is W, right? This is the same thing.
I'm sorry, yes, I should say U equals W somewhere and then talk about U. Thank you. So the dimension of the 8th exterior power is A plus B choose A as usual, because we're in R A plus B. So and that V should also be R A plus B. I misprints that. Okay, so dimension of U is at most A plus B choose A. Okay, so I'm just repeating the proof from before. So we're taking our nice subspace of the 8th exterior power of Rn, we're mapping it down to a subspace of the 8th exterior power of R to the A plus B. Okay. Right, so now suppose we're in this situation where the profiles are changing. So the A's are increasing, the B's are decreasing. Okay, let's try and do the same thing. So we'll start with some nice big vector space R to the N, and we're going to define a sequence of subspaces. So rather than throwing all my pairs at once and generating lots of vectors, I'm going to throw them in one at a time. And I'm going to have to think about what space I want them to sit in. So when I throw in AI, I'm going to be throwing in, okay, a set of size AI, little AI. So really, I want to throw in the vector that consists of wedging together its elements, so the basis vectors corresponding to its elements. So I really want something in the AIth exterior power. Okay, so at the ith stage, I'm going to want a subspace of the AIth exterior power of our underlying space. Okay, so how am I going to do that? So I'm going to start out W1. Okay, that's nice and straightforward. I'll just take the corresponding vector EA1, that should be A1. So just a wedge of elements in A1. And that gives me something in the A first exterior power. Great. But when I get to later ones, I may be sitting the existing subspace WI, that's in lambda to the AIV. I want WI plus 1 to move up to the AI plus first exterior power. So the sets that I'm throwing in, the A sets, are getting larger. The exterior power I need to be in is increasing. So what am I going to do? I'm going to have to move the subspace up. So WI, I'm going to have to lift it to a subspace in a higher exterior power. And we've got an operation to do that. This is the upper shadow operation, or the operation analogous to the upper shadow. So I just wedge with however many copies of V I need to. So I wedge AI plus 1 minus AA times with V. So I just wedge until I've lifted myself up into the right exterior power. And then I add in the vector corresponding to AI plus 1. Okay, so this is sort of a reasonably effective way to throw my vectors one at a time, increase the size if I need to. So it's like, you know, if you're thinking of the set system analog, you're throwing in the sets one at a time, and then taking upper shadows to move yourself up to the right size for the next set. So if you have a 1 set and then a 3 set and then a 5 set, you throw in the 1 set, take the upper shadow twice so that you have a collection of 3 sets. Now you throw in the 3 set, take the upper shadow twice. Now you've got a 5 set, throw that in. Okay, so we're doing the same thing in the exterior algebra. Okay, now let's note AI plus 1 and BI plus 1 are disjoint. So EAI plus 1. So what I want to show is that we have nice sort of, I don't want to say orthogonality because that's not the right word, but nice product properties. AI plus 1 and EBI plus 1, they have a non-zero wedge product as usual, because AI plus 1 and BI plus 1 are disjoint. And we're in a huge dimensional space, so we don't have to worry about that, about the ambient dimension. Okay. On the other hand, if I take WI, So everything I've got earlier, and wedge it with EBI plus 1, I claim that's going to be 0. So why? Well, everything in WI came from earlier EAs, maybe wedged with a few copies of V, but still everything was generated by earlier EAs. And EBI wedge any earlier, EBI plus 1 wedge any earlier EA is 0. The later BIs meet earlier AIs. So EBI plus 1 just wipes out WI completely. So we still have this sort of nice skew kind of annihilation condition. So sort of horizontally, nothing happens, and diagonally, everything gets wiped out. Earlier things get wiped out. In particular, this tells us that AI plus 1, so the new vector that we add, is not in WI wedge AI plus 1 minus AIV. Okay, so when we take WI plus 1, which was the WI wedged up enough times to get to the right level, and add AI plus 1 as well, we do actually gain 1 in the dimension. The dimension actually does strictly go up when we do that. Okay, right. So how are we going to control the growth of the WI? So given our AIBI, we'd like to map AI to an element of the AI exterior power. So mimicking the previous proof of, we'd like the AI exterior power of R to the AI plus BI. Okay, so remember previously we had A sets, we mapped them and we capped down, we mapped to a vector space, exterior power of a vector space of dimension A plus B. Okay, so we'd like to have dimension AI plus BI. We can't expect to be able to do that always, because AI plus BI, or at least not as simply, because AI plus BI is not fixed. The AIs increase, the BIs decrease. So AI plus BI might go up, it might go down, might stay the same. Okay, so the dimension of the underlying space that we want to have keeps changing and not monotonically. Okay, so right, so what should we do? So given our subspace WI, which is a subspace of the AI exterior power, let's just take a random projection to a space of the right dimension. Okay, so we'll take a random projection V from V, our big space, to the AI plus BI exterior power, and then see what happens to WI. Okay, so that's gonna go to the AI exterior power of R to the AI plus BI, of the AI plus BI dimensional real space. And we just track the evolution of the dimension of that as I increases. And I mean, you can say random projection, you can say general position. It's slightly, I find it easier to think about random projections, just so that you have no linear dependencies except for the ones that you're forced to have. That's the basic kind of basic rule. Okay, right. So again, we've got this projection, and the claim is just going to be that that evolves in the following way: the dimension of the projection of WI divided by the dimension of the underlying space. So it's the AI exterior power of AI plus BI dimensional real space. So it has that has dimension AI plus BI choose AI. So the fraction of dimension we get is at least the sum of 1 over, well, A plus B choose A summed over what you've done so far. So kind of it's accumulating 1 at a time. Okay. Right, and it ends up at most 1, so this must be at most 1 when we get to the end. Okay. Right. So again, I'm not going to give you too much detail, but I'll just say the key step is looking at what happens to the projections of the W. So if I look at pi of W I divided by, so there's got the fraction of dimension we get for the projection of WI. When I look at the projection of WI wedged up to get to the right height, to the right exterior power, the fraction of dimension should go up. That's the key thing. Okay, so I've got WI, and then I wedge up to get WI wedge okay, with AI plus 1 minus AI copies of V, or wedge AI plus 1 minus AI times with V. And I want to compare, okay, well, the fraction of dimension I get here with the fraction of dimension I get here, and I want to know I haven't lost anything in that fraction. So this is the kind of quantity we're carrying each time we go. If I can show that the fraction hasn't decreased, then that's a win, because I'm then throwing in another vector. I'm throwing in the new AI plus 1. That increases the dimension by 1, and the fraction of the dimension that's increased, that I've increased by, is just 1 over the dimension of the underlying space, which is AI plus 1 plus BI plus 1, choose AI plus 1. Okay, so this is really the key step. So what I'll just say, again, I'm not going to talk about it in detail. I'll just say if the sum is the same, so if n plus bi doesn't change, then this just follows from local LYM inequality for the exterior algebra. So this applies it. The other two cases, you have to do some careful averaging arguments. So you have to kind of get into the details of what happens. But again, the key idea is you're kind of tracking kind of shadows and that sort of thing. Okay, so there's detail here I'm skipping. Good. So that's at least a sort of sketch of the proof strategy. Let me finish with, I mean, this is one extension of the putting together these two types of condition. What more could we hope for? So you can play around quite a lot with different extensions, and this is sort of the nicest one that we found, I think. So we conjecture the following: so take a collection of pairs of sets, and the following two conditions. So as usual, the pairs are disjoint, and the skew condition. So if I have two sets with the same profile, I'm just going to have the skew condition between them. If I have sets with different profiles, I'm going to demand that I have both intersections. So AI and BJ they have non-empty intersection if either I is less than j, so I have the full skew condition. But then I get it the other way too when the sets have different profiles. Okay, so then it should be that the sum of AI plus BI choose AI inverse is at most 1. Okay, we've tried various examples. It does seem to work. We believe it, but we don't have a proof of it. So I quite like this conjecture. So it'd be very nice if somebody could solve it for us. Good. Okay, that's everything I had to say.
Great. Thanks a lot, Alex. It was a very, very interesting talk. I have quite a few questions.
Okay.
Yeah. So for this this conjecture, when you say profile, you mean an ordered pair or not ordered pair?
Yeah.
Ordered.
Yeah.
Okay. Actually, one random thought that I had about a similar statement is, what if, say, you require AIs to form an anti-chain? Would it be any meaningful? Because in the previous examples, you had a lot of containment, right?
Let me think for a second. I mean, yes. So one example you always have to contend with is you could make the first. You could take the standard extremal example for just all A sets and their complements.
Yeah. Well, there it's like it's an anti-chain, and then it's all
right.
But also,
now you can make the first B set just the empty, replace it with the empty set.
So can you say it again? So you're looking at all 2 to the n, well, 2 to the a plus b subset, pairs of subsets.
Take a plus b choose a sets. So just all pairs A set and its complement in an A plus B set.
Yeah.
Now you have equality in the condition.
Yes.
And now you could take the first. There's no condition on the first B set in your list.
Okay.
So you you could just delete, you can make it the empty set, and now you've thrown off your, not by very much, but you've thrown it off a bit.
That's true. And what about both A family and B family being an anti-chain? Because that forbids that thing, which is a natural generalization of having the same cardinality, I guess. I guess that is that falls into this category. But yeah, okay. And another thing is this. So you showed this example for n+1. Can you actually show that this is tight? This sum is at most n+1. Does it follow from your result actually somehow by clever, splitting into some orders?
I know it's trivial because you've got all pairs. So if you threw in any other pair, you get a repeated.
But your ground set is not. Wait, your ground set is not fixed, right?
Right, but if you took a bigger subs, I mean, it's n+1 where n is the size of your ground set. So you can just make it arbitrarily bad.
No, okay. What I mean is, say for example, you fix the size of A plus B, maybe, or maybe I don't know. Maybe it does make sense. But if you fix the size of A plus size of B, and then you ask this question.
Yeah, but then you could split by.
Yes.
I mean, you could split by the size of A, and now you get.
Yeah. Okay, that's true. Yeah. Okay, and one more question is, where did you use the condition on B's? So did you use in this last averaging argument?
Yeah.
So that's okay. And okay, maybe I should take a pause. Maybe someone else has questions.
Yeah, I have two questions.
Great, Grisha, go on.
Okay, so first let's start with just your version of Wedge-Corrado theorem. Yeah. And my first question is about, have you tried to translate your version for in the setting of exterior algebra to the Wedge-Corrado for sets? Because in some sense, if you consider the space subspace in the exterior algebra setting, yes, this is a linear combination of decomposable vectors, and the decomposable vectors in some sense corresponds to the real ground set, and in this direction. So perhaps you say something like this, that if we have several sets and I don't know, and we take with some coefficients intersection, then we might conclude something. So,
okay, no, it'll be interesting to find something. I mean, I guess you'd have something about fractional sets, or
something about fractional sets or whatever. I mean, because it seems to me that your result, it's more general. It's not just a direct translation from the setting of sets to the exterior algebra, because we have these ugly spaces, yes, subspaces, right? Not everything is decomposable.
Yeah, no, it's a nice question. I think it would. Yeah, it would be. I don't know whether you get something that would have a nice consequence. So.
Yeah,
So you can,
for some subspaces,
possibly, yeah.
It would be nice to find something if there is something, of course.
Yeah.
But the second question, that again with Wedge-Corrado is the most simple case for me, and that in there it's one has to consider R at most n half, yes,
yeah,
and but in the space of linear, these exterior vectors for k forms or whatever are forms, there is Hodge operator, yes, the just duality between the k flat and the n minus k flat, where n is the dimension of the original space.
Yeah,
and of course there is still there is no sense to ask about the Wedge product of of two n minus k sets are R sets, but probably there is some geometric description of this situation that doesn't use this. So, I mean, just simply, what does the dual statement say directly for the dual spaces? Probably some geometric consequences.
So if you take an intersecting, well, so to say, intersecting family on a layer below half, and then you use this Hodge operator, and then you get some similar statement that
I don't probably it's nothing, but I don't see the geometry like instantly. Again, there is no sense to ask about the wedge product of two such elements, because the dimension will be bigger than n, and it's 0. But still, now we have some weird spaces, and probably there is some geometric description of the same.
Well, so go on.
Sorry, I just wanted to say that combinatorially, of course, there is meaning to this kind of things, because you can also look at sets, at families of sets where the union does not cover the whole ground set. So maybe this is what maybe would happen. Something about spanning. I don't know.
Yeah,
spanning things.
So I think, I mean, Elizabeth may be able to help me with this, but I think this is in some sense what we're doing with our proof for the equality case. So Elizabeth, do you have a comment on Hodge?
Yeah, no. So this is all tied into the question of really what is the complement, and sort of, for sets, the complement lives in the same collection of sets, right? It's on the same ground set, but the most natural interpretation of the complement here lives in the dual space. And I think that the work that we're writing up right now, there are a lot of computations exactly along the lines of what's being suggested here. So yes, it's all true and it's all interesting, and we're writing it up. Or we're writing up pieces of it. There are others, of course.
Okay, it's good news for you. I would say like this. Thank you. It was a very nice talk.
So any more questions?
I have a question. Did you try to apply your method to more than two families with more than two subfamilies?
Oh, right. Yeah. So there's a nice theorem of Noga-Alon where he has sort of multipartite families. Yes, that's on our to-do list. So we haven't chased that. But a good question. Yeah.
So someone else?
Which conditions do you think can be more relaxed? Or you think it's
for the two
exact?
families? For
Hmm?
the two families theorem, you mean? So
which
is your question? Can you what conditions for two families theorem type results can you relax further?
I mean, maybe you have some ideas about other conjectures.
You mean for the two families setting, Rita, or for the?
Yes, two families.
Okay. No, excellent question, and one we spent considerable time playing around with. So we tried quite a few different things, most of which we found counterexamples to. So it's surprisingly hard to check, and you can run little programs that check some things. I don't think at the moment we have a. I mean, what would be kind of most satisfactory would be a kind of optimal condition in some sense. I'm not sure we have one. I mean, the conjecture is, I think, the nicest, stronger version that we can think of at the moment. Yeah, maybe there's something more you can do, but whatever you do, you have to design it to avoid that catastrophically bad example where you get all pairs.
And actually this condition for I smaller than j, there is no hope even for equal sized sets to relax it further in any way, right? So this is in some sense like the minimum that you should ask. Or in general for this fixed size A and B, are there any other nice conditions that one can impose? I mean, or does it really all the time it boils down to this independence thing? Whatever thing would guarantee you this linear independence if you do it in some order? Then...
So I mean, there are other things you could do. So you can have, for instance, so there's an old, if I remember correctly, an old resulted question, then result of Tusa, where you have AI and BJ, and you have one of the two, and you can choose which, and then you give up a little bit.
Yeah. And there the answer is not known, right? The exact answer is not, or is it?
I don't think so. And you could try and do the same thing, and we haven't tried to do that. Yeah, that's another thing we haven't would be interesting to chase. Yeah, to get some.
I mean, the underlying linear independence argument does really depend on having things in an order, and the full skew hypothesis gives you a full order. And
and so what about the Kruskal-Katoda statement? Because I mean it's like local lim but better, right?
Yeah. So I think there are a lot of people in algebra who think of the Kruskal-Katoda theorem as being like their theorem, and you know, and it's a statement about the Hilbert functions of ideals. And you can work that out for ideals in the exterior algebra, and it's in the book by Herzog and Hibby on monomial ideals in the way that algebraists like to talk about it.
Okay, but is it just a quick check? So does it imply your local lim, for example? Because normal Kruskal-Katoda obviously implies local lim. So is it exactly the same notion of upper and lower shadow?
I'm going to say yes.
Okay.
It can be made to be exactly the same.
Yeah, you know, what are you doing when you wedge with 1 power of v? You're looking at which elements in the ideal are in the next level of the grading in the exterior algebra. So.
Okay. Great. But it's much simpler to write down the LYM. So that's why I run it that way around.
Great. Any more questions? Well, if not, then thanks a lot, Alex. It was extremely interesting, and thanks to you and Elizabeth for all the comments. And
okay, thank you very much. Thank you to Elizabeth, whose grasp on the algebra is much better than mine. So.
Great, and yeah, hope to see you sometime live. Not that.
Yeah, no, in three dimensions at some point soon, I hope.
yeah, some point soon. Okay. Bye, everybody.
Okay, thank you.